Alright, today let's talk about doing implicit analysis inside LS-Dyna. And what I like to do is to do this presentation or to do this video in the context of Ansys Mechanical. Also, obviously, also having its own implicit solver. Uh, I think it's a good idea to try to learn how to do something new within the context of how to do something that you already know how to do, right? That's a very good way to learn. So what I'm going to do today is that I'm going to talk about the general concept within implicit analysis, and I borrow some information from the documentations for mechanical, and I'm going to use that context to talk about the different implicit control cards, and you will see how they are basically the same thing. They just have a different way, different implementation, but the basic idea is the same thing, right? And then I have an example model prepared, which I'm going to talk about doing a very simple model like this inside both mechanical and LS-Dyna, and I'm going to compare the differences. Um, Now you can sort of see, right? I'm going to show the different ways that we can set up a Dyna model to see look at the solve time compared to mechanical itself. And then, I want to do some correlation between the setting inside mechanical and the setting inside Dyna. And you realize they're very, very similar to each other, at least within the context um, of the problem that I have generated, right? Now the example problem is very easy to understand. What I think is the most important thing to learn about setting up implicit analysis, right, is to understand the key concept that we want to be able to know in order to properly set up an implicit model, right? Of course, within other things like contact, there are other things to know more about in terms of damping, in terms of contact. But from a simple static structural analysis, let's look at what we can sort of grasp and then to form that basic thought structure for how to do an implicit analysis inside Dyna. Okay. All right. So a very simple concept, right? I'll full screen this and I'll switch. I think for the most part, right? Dyna is used for explicit analysis, right? In which you usually solve the problem directly, taking a very very small time steps. Like these are like a stable time increments. Usually you don't have to check for convergence, and you can handle problem that's highly nonlinear, but usually very short durations. And these are very good type of problem for explicit models, right? Now, when we go into implicit schemes, when we want to solve a problem that's much much longer in duration, right? Such as for example earthquakes, right? Earthquake is a time domain dynamic analysis. That's clearly not going to be suited for an explicit method because it takes many seconds to resolve it, to go through the full sort of sequence of the input load. So for implicit analysis, right? Sometimes we want to handle like a quasi-static analysis that's also very long in duration, so we don't want to capture, we don't want to solve that explicitly. So really, with an implicit scheme, right, we're essentially allowed to take arbitrarily large time steps, right? Because the solution is always going to be unconditionally stable. But what we have to do is to understand how to achieve convergence, right? Which is a minimization of the system level energy or the system level residuals that we want to be able to minimize within an implicit method. And then, within a different solver, there are tools that allows us to do that. There's, sometimes we have default settings that can handle a lot of different applications, right? But we want to understand a little bit more about the different knobs we can turn to achieve a good solution within an implicit scheme. Okay, so the key concept I'm gonna go over, right? So the Newton-Raphson method is the first thing, along with the concept of convergence, right? Just look at very briefly what that really means. We're also going to look at a basic overview of the full Newton-Raphson versus a modified Newton-Raphson. This concept exists in both mechanical as well as LS-Dyna, right? And lastly, we'll talk about line search and arc length. Our line search methods are a way to achieve optimal time step within the algorithm itself, and the arc length method is allow us to sort of achieve some stability in problems that are slightly unstable, such as one in which you have very small amount of load, but with a very large displacement that follows, right? Okay, I mean, in a basic static problem, right, what we're essentially doing is solving the relationship between the external force and the internal displacement, the displacement at the nodal level, right? And what creates that relationship is essentially the stiffness matrix that we're formulating for the entire system, and that's in essence what we're doing. right? So when we solve this kind of problem, right, within the algorithm itself, obviously you're going to be solving a system of linear equations, or rather system of nonlinear equation in this case. And then what we're essentially doing is to look at a residual that's a form of out of balance load that we're essentially trying to measure. And we'll want to make sure we iterate through the system such that that residual falls below a threshold. That in essence is the concept of convergence in the simplest sense that one can sort of phrase it, right? Now, if we look at the Newton-Raphson method, right, this is the kind of curve is something that you can sort of see. This is within a single iteration, right? You'll basically do a search and calculate a search and calculate a loop. You'll try to look at the restoring load versus the applied load, and looking at the displacement that's generated and added to it, and look at the residual. And you have to keep doing it until the residual is small enough such that you essentially achieve so-called convergence. Now in Dyna, right, the primary way in which we're looking at this one is through a displacement norm versus the total displacement, and then there's also the energy component that we're also look at in the Dyna. In mechanical, the energy portion is usually not looked at direct, at least by default. You can look at things like displacement and force residuals, but the general concept is actually, in my opinion, exactly the same that what we're looking at. Now, with a nonlinear problem, right, usually what happens is that you have to break down the each iteration into additional substeps to allow us to take a smaller increment so that we can actually find the solution within that smaller increment, right? As opposed to taking a lot of iteration across a larger step, you're going to take multiple smaller iteration across multiple substeps to allow us to be able to look at this type of find convergence within this type of low path, right? Now, the idea of a full Newton versus a modified Newton-Raphson iterations, right, procedure is really just how many times does the stiffness matrix get reformed within that process, right? So they call it a full Newton when the stiffness matrix reformation happens only one time per iteration, and if it's modified, it means it happens as an iteration per it happens one time per n iteration. So that could be something that's not going to be basic happening once per iterations, and that's really in essence of a full Newton-Raphson iteration. Is this full Newton-Raphson iteration is usually a lot slower than a modified version of it, right? But then sometimes this is necessary when you have a highly nonlinear problem. And sometimes if you have status changing problems like a contact non-linearity, that's also become necessary. In mechanical, I think this is sort of run by default, right? In Dyna, we will have to define exactly what we wanted to do, and I did some quick explanation in this example video, right, to show what kind of behavior I'm observing when I changed it from a full Newton to a modified Newton-Raphson procedure, right? But whatever choice you do, right, what really happens in the background is that we're essentially trying to uh, 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 get to convergence, right? And what's usually checked are things like are the norm of the residual itself. Norm is like the Euclidean norm, which I think is like the square root of the square of the vector itself, which is the thing that we're essentially looking at. And then you can look at the infinite norm, which is the maximum of your residual. You can also look at L1 and L2 norm. These are the basic came from the mechanical documentations, right? You can also look at a convergence based on the energy calculations, right? This is not really commonly used inside mechanical. But whatever residual we look at, the key idea here is that it has to fall below certain threshold, and this is internally determined inside mechanical. In LS-Dyna, you have these default value that you can try, but you also have a lot more freedom to really adjust what you want to use. So we always want to be very careful. Like in mechanical, like Ansys Mechanical user will rely on the default all the time, right? But there are certain applications, certain situations in which we want to be careful with the default value to make sure we understand exactly what we did. And there are other ways within a Dyna environment that allows us to really adjust the threshold for convergence to control the relationship between how many iterations it will take to get a convergence versus the cost of the simulations. Right? Sometimes accuracy is achieved at the expense of the computational cost because it requires additional number of iterations to get to convergence. That's the kind of things that we can sort of play with inside Dyna. But within mechanical, it's sort of internally determined for you within the program. It makes it easy for users. Okay, so line search is essentially a way to find a minimization point within the potential energy of the system while keeping track of the residual, right? So you essentially look at the residual value as you iterate through it, and it's essentially used to determine the optimal time step within the Newton-Raphson iterations, right? So you think of it as a way where you essentially apply a multiplier to your quote unquote to your equation, such that if we adjust the line search parameter, we can adjust the displacement, the total displacement, and that allows us to find the optimal time step to take given the observation of the energy of the system and given the observation that of the residual that we're tracking. So if the residual is increasing, right, this thing can be used to sort of adjust the time step internally within the iterations to help you get convergence faster. So think of it as a sort of a way to more intelligently get into convergence and saving some computing power, some computational time. Arc length method is really a way to trace the complex path of a low displacement response, right? So it's a way to get convergence when you have an unstable problem, such as one where you have a small amount of load and generating a very large amount of displacement. So I've seen this being done for like post-buckling behavior, for example, that you can usually do. Stuff like this, I think is in mechanical. I think you turn it on yourself. In Dyna, there's an option that you can also do to turn this on. But just know you look into this when you have a unstable problem, right? Small load, large displacement type of problem. This might be a good option to have as well. Okay, now understanding all of that, right? So remember key thing, right? Understanding all of that is really just these 5 different concepts, right? Your Newton-Raphson method is a way in which you can iterate through the problem to get a convergence within each time step. And the way you go through the entire problem, you can either use a full Newton method or use a modified Newton method. That just depends on how many times you reform the stiffness matrix. Line search is a way to find optimal time step within that Newton-Raphson method. Arc length is for unstable problems, right? That's the quick summary of the entire thing I just talked about. And you can find a lot of this information in the documentations. So let's look at how Dyna handles these concepts within its program, right? Now within LS-Dyna, right, the entire so what I've created is this template for implicit control cards. And I did this with a parameter card, which has all of these key parameter parameterized, key value parameterized. These are the things in which I also have a comment about exactly what they do, right? The initial time step. This is my min-max. This is my range of my time step. This is the solver I'm using. This is whether or not it's a dynamic or a static. This is the default residual. This is the solver, direct versus iterative. This is like the direct solver in Ansys Mechanical, and then when it's 2022, that's like I just lost the word. The iterative solver within the mechanical. The IMAS is whether or not it's a static or dynamic, right? The limit is that full Newton iterations or modified Newton-Raphson iterations. And then the gamma and beta is like a damping characteristic that's used with the dynamic analysis. So these are the key parameters that I have determined that should change from one problem to another. There are a few other things down here that can change that can also be further parameterized. But for now, this is my template for each implicit problem that I'm going to be doing, right? Now there's a lot here. So what I've done inside the presentations, right, is that I've essentially gone through this one by one to put together a very good sort of thought structure, right? My video is always about building repository and building structure for how I think about problems, right? So within implicit analysis, right, so the first thing that I want to know is essentially your initial time step size, which is this dt0 right here. This tells you what kind of time step do you start with, right? So this is no different from the initial time step inside the static structure analysis inside mechanical. Okay. The IM flag is essentially a way I use a load curve to represent it, but if you set it to 0 to 1, it's implicit. If you set it to 0, it's explicit. So you can actually do a switch. I have a video about doing this switch, but basically I use the negative value of a load curve and I set everything to 1 for implicit analysis. That's all I'm doing. Okay. The second thing we want to look at is the way auto time stepping is going to work inside Dyna, right? So in mechanical, we also have automatic time stepping. If you know what I'm talking about inside analysis setting, right? The iauto, IE, ITE, OPT, ITE, WIN, this is basically represented by this graph right here, right? So you start with an optimal number of iterations that you want to go for per time step, right? Let's say I wanted this to be 20. and then then itewin is my plus minus of that range. So if I did this to 10, it basically will auto adjust the time step between 10 and 30 iterations. If you go above 30 iterations, if you go above the highest range of the iterations, it's going to bisect the time step in the next time step, right? It's gonna bisect the delta t in the next time step. And that's essentially a way for Dyna to do auto time stepping, right? So you can actually control the behavior of when does the LS-Dyna auto time stepping changes the time increment. If you want to make this number really big, you can just make this number really big, so it never really dissects, right? It will just keep solving and solving and solving, right? So this is basically a way in which you can directly control auto time stepping inside Dyna, right? And of course, if you make it too regressive, then it's just gonna take longer to solve. So there's a lot of optimization you can do on a per problem basis to make the problem solve faster. Next thing is, there's a bunch of different solver within Dyna. This nsolve parameter right here. This basically defines all the solver that you can invoke, right? The most common usually one is for a purely linear problem, you use equal to 1, right? For a non-linear problem, you can just use 12. The 6, there's a couple different other ones that you can use that you can look at a comment with, but basically 12 is the more recent one, and it's actually very, very good. It also invokes arclength 3, but it's essentially what you use for non-linear problem, right? So one's with contact, one with material nonlinearity, one with large rotations, right? So these are the kind of things that you can use for those nonlinear problems. So remember, 1 and 12 are the most commonly used ones. The other ones, look at the documentation for on a per application basis. Okay, so the other parameters that are very, very important in the control implicit solution, right, is the I limit is basically where you control whether or not it's a full Newton-Raphson or a modified Newton-Raphson. A full Newton-Raphson, you set this to 1. A modified Newton-Raphson, you will set this to some number in which you will go through that many iterations before it reforms the stiffness matrix. Right, so usually it's much slower. It will take longer to get a solution if you set it to a full Newton-Raphson, because every time you reformulate the stiffness matrix, it takes more time from the solution to actually do that. So it takes longer to do a full Newton-Raphson, but it's better, for problem that you might run into the divergence for like a highly nonlinear problem. Using a full Newton-Raphson actually helps. Now the max ref here is the max number of stiffness formation per time step. So I think you'll get to divergence. You'll basically stop the solve if it reforms so many times. The DC toe, EC toe, and RC toe are essentially your residuals, right? So displacement residual, energy residual are the most commonly used one. The R residual are the force residual, right? This one is usually set to some really large number inside Dyna as default. You don't really use it. We can certainly use that, and there are guides within documentation that show you when you can use that. But for most common problem, we can just set DC toe and EC toe to the default value, which I think is like 0.01 and 0.001, right? That allows you to basically get to some meaningful convergence. This is very much the default value. You can always change things around. The NL norm here, basically looking at, are we looking at the problem only from a translation standpoint, or do we want to do a combination of both, right? So usually I do a D norm of 2 instead of D norm of 1. D norm of 1. D norm of 2 is easier. For problem that involves rotation, like mechanical will automatically generate that rotational residual, right? In this case, Dyna, you have to basically define it, so you know your problem, you can change it. And of course, divergence right here is that every time you diverges, you can actually set the problem where every time you see a divergence, which is when the residual becomes bigger and bigger, right? When that's detected, it's going to reform the stiffness matrix right away. So that's a great way to save time. So instead of reaching the divergence, you're gonna detect divergence during the iterations, and then reform the matrix right away, right? The I stiff right here is basically, do you want to reform a stiff matrix at the start of each time? Usually that's required. So usually that's set to yes, right? And then at this here we can also check for penetration in the contact. So these are the things that are very meaningful parameter, right? I parameterize the most important one, which are the solver I'm using, and then whether or not I'm using a full Newton or a modified Newton-Raphson, and then I set my parameter for my residuals, right? And that's the key thing I'm setting as a parameterized. Everything else I'm leaving as sort of a default to what it is. I usually do D norm of 2, actually not 1, but in this case, in this screenshot is set to 1. Now, now print equal to 3 is very useful to get really good information. Get really good information in terms of the problem with like divergence, for example. And our norm equal to 2 is usually what's done because you are doing that as a function of total displacement. In problem with very, very large displacement, this should be looked at, right? Because you are basically looking at increment over the total as opposed to over the current time step. So something to consider. Okay, that's a lot of information. Obviously, like the key here isn't to remember everything. The key here is to get the key points out, which are these 4 parameters, right? You're defining your solver, you're defining your tolerances for convergence. Everything else, look at the documentation as you go for each problems is the best way to look at it. And here is where we can also look at the arc length method, right, and line search method. These are things I'm not gonna go over too quickly, but you can sort of see this line right here is your arc length method. This line right here is your line search method. So you can define your arc length method and your line search method inside the control implicit solution card, right? Much like you need to do inside mechanical. Sometimes you may just make into like program controlled defaults. All right, and of course we talked about the solver stuff earlier. This is the I solver, which is not the N solver, the I solver, which is the which is whether or not you're using a direct solver or iterative solver, right? The PCG solver, the precondition conjugate solver, or you're using iterative solver. So this is the same as the direct versus the versus the PCG solver inside mechanical. Usually you choose either 7 or 22 for the kind of problem you're solving, right? Very much similar to what mechanical does. And of course, lastly, if the problem itself is a static analysis, you set I mass value to 0. If it's dynamic, you set it to 1. And the other ones is for like a combined with modal analysis. Gamma and beta is for the new arc time integrations, right? This is for adding some damping to the systems. You can also use these damping cards to do so as well. Okay. And of course, in here, the key parameter here is the I mass parameter, right? You set it to 0 or set it to 1, given whether or not it's a static problem or a dynamic problem. Okay, so this is the basic concept. It's a lot of information, right? So it's obviously not intended for one to fully absorb in first view, but I created these slides so I can have a reference to come back to later should I want to remember what I did, right? Because this is really the nature of these videos for me, for myself, is to create like a repository of knowledge. But a quick demonstration of the problem, right? So over here, what I have is a very simple model in which I basically have, oh, did I? Oh, I did. Yeah, I guess my solution was gone, but I guess I can still show it without having to resolve. But you can sort of see in this problem, all I have is I have an arm that moves forward and comes back. That's all it is to it, right? Problem like this is pretty simple, right? So you can sort of see I have the stress right here. This is the max stress over the entire time duration, right? And then all it is, right? I fix on the bottom here, then I apply a displacement over here. Then I have like a 2 different material applied to the arm and to the little bump here. This is like one of the baseline for my training material that I've created before in the past. Very, very simple problem. There's nothing really to it. What I wanted to show with something like this, right? You know, if you look at my analysis setting, everything is pretty much I'm using a direct solver. I actually have weak spring turned on. I really should have turned it off. I have some auto time stepping generated. I'm not changing my convergence criteria in any way, right? I'm not changing my line searching in any way. I'm just using the workbench default. And then this is the stress I'm getting, right? No problem here, right? And it took about 5 minutes and 38 seconds to solve. Now, if I look at the same problem inside Dyna, right, the setup is pretty similar, with the exception that I'm applying a remote displacement, which is gonna transfer to a boundary prescribed motion type of card, and I'm constraining all the degree of freedom except for x, which is along this axis right here, right? And then in my section, this is a mesh with a 10-noded tetrahedron elements. And then I assigned a section card to it to define outform 16, right, which gives me the 10-noded tetrahedron element that I want to use. This is recommended for a tetrahedron element for this kind of problem. The implicit control card, which is copy pasted from my template, right? I adjust the behavior of my cards right here, then I copy paste into the solver. This basically handles everything. So all of this right here is handled within the template. I just adjust some value before I copy paste over. Then I have my default control cards, and I have my default database cards. All of these things are set so that it's suitable for the problem at hand. I have my parameter which define all of my time history and then my D3 plot frequencies, right? In this case, You can see the setup is very similar to each other. I have my contact between this, and then I'm just pushing it the same distance as before, right? And I'm gonna look at the stress on this thing. That's really it. There's no trick to it. In this problem right here specifically, I actually did a couple different iteration of this, right? So let me show you in the presentation itself. I'm gonna go back to the presentation itself, right? So first thing you can sort of see is that the stress, this is the dyno side, this is the mechanical side. You can sort of see, so you see that element I selected, I basically plotted over time. You can see the peak stress is around a little bit less than 10, maybe 10.6, 10.7, 10.8. On the mechanical side, I probed the nodes around the same area. The stress is around 10.3, 10.4, right? So you get a pretty much the same stress in the same location between the dyno model and the mechanical model. Basically telling you that you have very comparable results in both simulations, right? That's first thing. Second thing, what I did was I took different parameter within the dyno side to show how it behaves in relation to the mechanical. So the mechanical solve, right? Default mechanical solve took 5 minutes and 38 seconds, right? The first time step, if you don't recognize what these are, basically in this case, I use a modified Newton-Raphson for 25 iteration before stiffness matrix update, right? I use the direct solver, then I do a static analysis. In that case, I solve it in 4 minutes and 50 seconds. If I use a full Newton-Raphson iterations with the static analysis and then direct solver, it's finishing in 12 minutes. So almost more than double the time it took to solve. In here, if I use a dynamic analysis, if I turn on the dynamic analysis by changing Imax to 1, and I use the 0.6 and 0.38 gamma and beta value, which is recommended for quasi-static analysis, I can solve this problem in 5 minutes and 31 seconds, very similar to the static structural problem, with the exception I have a slight amount of dynamics added to it, right? Now, if I don't use the correct value of gamma and beta, I just use the default, which is 0.5 and 0.25, it actually fails to converge, right? So this really tells you you can't just use the default value for implicit cards in Dyna and get it to work even for the simplest problems. You have to know what each of these key parameters really mean, how to adjust it, right? So if you look at my control cards, right, the control cards I've generated, I've taken quite a bit of effort to make sure I'm using the right cards for my problems, so that I'm using it and I can easily adjust it for different kind of problem. Then the comments itself allows me to basically adjust so that I can adjust on per application basis. And last but not least, right? So if you look at the actual comparison between mechanical and Dyna, these are actually mechanical windows, right? So direct solver corresponds to that. The time step control corresponds to this card. The Newton-Raphson control corresponds to basically this value right here. Yeah, corresponds to like this value right here. These are the residuals that you're defining right here, and then line search is being defined right here, right? So everything you have in mechanical, you also have in Dyna side, with the exception that you're using it mostly on a car basis. Now, no, lastly, I will recognize that Workbench has a implicit, I think it's over here. I just don't like using it. I think it's silly. There is an implicit control somewhere in here, if I know where it is. There is an implicit control in here, I believe. I just don't remember where it is. Oh yeah, right here. If I change this to nope. Well, I can't find it. But basically, there should be a way. I think there's a way inside here where you can do all the implicit control stuff inside this setting. But as you can see, that's not really advisable, right? It's so much easier to do inside a text editor. There's no amount of development they can do inside Workbench that's gonna make it easier than what I'm seeing on the screen here, right? As long as you know what you're doing, this is like looking at code. But after a while, you just know what you're looking at. It's no different from looking at anything else. You just recognize what you're looking at on the screen. This is much easier than even the mechanical method. All I have to do is change a couple numbers, then I'm done, right? For each whatever problem, I just copy paste it into a text into here, and I'm done. And which is why I really recommend having your own implicit control card templates for your problems for implicit problem inside Dyna, because that really is the foundation of your being able to do implicit analysis inside LS-Dyna correctly and with ease, right? Okay, I hope this helps. It's a longer video than usual, but I hope it helps. Thank you very much.